So we are going to see what asynchronous counters, registers, and few questions. See, this sequential circuit, if you ask me for gate, this is a very conceptual topic and a lot of questions can be asked from here. But if you are preparing for PSU kind of exam, then very simple questions. It will be asked based on the counting sequence, or they might ask you by giving a counter that whether it is up counter, down counter, that you need to identify basically what type of counter it is. Okay, or they will ask you what is the mod number or how many unique states are there in a particular up or down counter. Okay, so let us then understand. In our previous session we have seen how to actually see the counting state of a synchronous counter. So usually synchronous counter we take help of next state equation. Okay, we take help of next state equation to calculate our counting sequence. But in asynchronous counter, our all the flip flops, so basically we will use JK flip flop in toggle mode, or we will use toggle flip flop in T mode. Okay, so basically over here we have what asynchronous counter. In asynchronous counter, the output of one of the flip flop is the clock for the next subsequent flip flops. Okay, so here we take help of toggling mode of JK or T flip flop. So let us then see. And I have also told you that synchronous counters, it is either up counter or down counter. There cannot be any random counting sequence. Okay, so in the first session when we were speaking about difference between asynchronous and synchronous, I have talked about that. Okay, so Srihari, you want to ask something?
Have you started sharing any slide or what? I haven't
Oh,
seen.
oh. Okay. Sorry. So I haven't started my screen sharing.
Okay, okay.
Okay. So now I was telling what? That basically in synchronous counter, we take help of next state equation to calculate our count sequences. Okay. But in asynchronous counter, our flip flop, it works in your toggle mode only. If it is JK flip flop, input will be what? It will be 1 1. Or if it is your toggle flip flop, your input is going to be 1 1. Okay. So asynchronous counter, we usually have count sequence either up counting or down counting. In synchronous also we can have up down counting, as well as we can also have random count sequence like something like this: 1 2 3, 3 to 5, and again from 5 to 1. We can have such counting sequence. But in asynchronous, count sequence will be from 0 to 1, 1 to 2, 2 to 3. If it is a 2-bit asynchronous counter, either it will be like this, or we will see how to make such kind of, means like this. So one state is missing, still we can make what? We can make such kind of counter over here. Okay, so we can make counter like this. We can skip a step over here, means we can skip a counting state over here, but altogether it will be always what? It will be like 0 1 2, or it can be even 0 to 1, like this count sequence. We can never have a count sequence where we are skipping one of the states in between two intermediate states. We cannot do that in your asynchronous counter, whereas in synchronous counter we can do that. Okay, so now let us study about asynchronous counter. Okay, so asynchronous counter, it can be either, they are usually edge triggered. In our syllabus we have edge triggered only. So either it can be negative edge triggered or it can be positive edge triggered. So how do I identify basically a negative edge and a positive edge triggering? So if you see something like this, okay, so if this is your flip flop, and if you see something like this, This is your negative edge trigger. So whenever the flip-flop encounters the negative edge of clock, it will change its states, okay? And a positive edge trigger flip-flop, it looks like this. So this is what? This is your positive edge. So a positive edge trigger flip-flop, it will be what? It will change its states whenever it encounters the positive edge of the flip-flop, okay? Positive edge or rising edge also sometimes it's said. Okay. So here I have taken what? I have taken negative edge. So first identify the negative edges. You can see this is one of the negative edge, another negative edge. This is one more negative edge, and this is one more negative edge. Now this clock cycle means clock signal. It will be go on. It will go on and on. Okay, but here I have taken a finite number of clock cycles. Okay. So initially, let me assume over here that Q is equal to 0. That initially the flip-flop is reset. So if that is the case, if this is your clock cycle, means clock signal, so I have assumed initially Q to be 0. So this is 0. Now you can see at this precise moment, we have what? We have a negative edge of the clock, and this flip-flop, it is working on your toggle mode. It is working in your toggle mode. So if it works in toggle mode, then if your present state is 0, next state will be what? It will simply toggle to where? Previously it was 0, now it will toggle to 1. And in between the clock edges, the flip-flop is going to hold the value. Okay, it is going to hold the value. So this will continue to keep in 1. Now see, once again we encounter a negative edge of the clock pulse. So present state was 1. As this flip-flop is working in your toggle mode, as j is equal to 1, k equal to 1, so that is why toggle mode. So immediately what will happen? Your next state will be the complement of the present state, or it will toggle. So present state is 1, next state will be 0. And this cycle will keep on going. Okay. So here you can see this is 0, then 1, again back to 0, and this cycle will keep on forever going on. Okay. So this is what? This is mod 2 up counter. Okay, mod 2 up counter. So this is when you take the output from non-complemented output. If you had taken output from the complemented output, so this will be what? Means if this is 0, no, complemented will be what? Complemented will be 1. So this will be like this. So this is 1 0 1 0 1, and this will go on and on. So this will be what? 1 0, like this it will go on. So this will be mod 2 down counter. Okay, so this is the very simple, means what you can say, the simplest asynchronous counter that we have constructed using a single flip flop, the single JK flip flop. Okay, fine. Now next, here I have combined two JK flip flop to form a 2-bit counter. Okay, 2-bit counter. Now let us see the counting sequence. Okay, first tell me, means here I haven't marked that. Okay, let me assume this is flip flop A, this is flip flop B. So which one is MSB, which one is LSB? Which one is a MSB? Which one is LSB? Mangesh, Srihari, anyone want to say?
QB is MSB.
This one you are telling MSB?
Yes, yes.
Okay. So this will be LSB then according to you. And why do you think so?
Like if you're writing that uh, based on that sequence, I think the frequency division takes place like in the LSB side, the changes are 0
Ye-
1 0 1, and
Yes.
in the MSB side, it will take one this output to reach the second flip flop, and it
No,
will
no.
change every.
I am asking. See, you are correct, partially correct. What you are telling.
Okay, okay.
So frequency, you are telling that here it will be 0101 like this. So here also this will be 0101 only. Zero
Uh,
one zero one. Okay.
I mean, it will take some time to reach the second flip flop. Only after the first output we
So
get
what will
01.
happen means if it is taking some time to reach, then what is the issue? What is the problem in that?
Uh,
Okay, it's okay. I will explain. Okay. So okay, you are correct. We will see. At the moment, just write this is MSB. This will be LSB. Now you can see both the flip flop are negative edge trigger. It can be positive edge also. Okay, it doesn't matter. I will actually tell you the trick how to identify the counter if it is positive edge, negative edge. I will tell you everything according to your objective paper. Okay. At the moment you just understand, because if I don't tell you all this, na, then even if I make you means mug up all the theory, you won't be able to remember. So look over here. This flip flop is what? This is getting the external clock pulse. You can see clock. This is your clock. This is your clock signal. This is what? This is negative edge triggered. Okay, fine. And output, normal output of this A flip flop is acting as your clock for your flip flop B. This is also negative edge. So the negative edge of the output of flip flop A is acting as your clock for flip flop B. Okay. So first let us draw the output of flip flop A, QA. Okay, first let me draw QA. So if I want to draw QA, so let us assume that initially QA is equal to 0 and QB equal to 0. So if this is the case, so this is 0 initially. The moment we encounter a negative edge of the clock, this will toggle to 1 and this will keep on going like this. Okay, fine. Now let us identify the negative edges, because as this output, this is what? This we got over here, QA. And you can see the negative edges of QA act as your clock for flip-flop B. So let us see the negative edges. So you can see this is your rising edge. This is your decaying edge. So this is one of the negative edges. Another negative edge, negative edge, negative edge. Now look. So I have assumed QB to be also 0. So only at the negative edges it is going to toggle. Okay, fine. So this is what? This is QB. This is QB. So now for each of the clock cycle, this is one clock cycle. This is another clock cycle. or you can say this is not one clock cycle. This is 0th clock cycle, this is first clock cycle, this is second, this is third, this is fourth, this is fifth, this is sixth, this is seventh. Okay, fine. So initially the states I have assumed to be 0, 0, and that is evident over here also. Now this is 0, 1, 1, 0, 0, 1, 1, 0. And over here it is 1, 0, 1, 0, 1, 0, 1, 0. Fine. Now, how to identify the MSB and LSB in a count sequence? So let me show you that. If someone asks you, okay, so what should be the proper answer then? Now, if I ask you, what is the MSB and LSB over here? It is very simple. You will say that if this is A, this is B, this is C, then you will obviously say C is what? C is your LSB and A is what? A is your MSB. Now, why so? See over here that your MSB, it toggles the least number of time. It toggles the least number of time. You can see over here that this is toggling only after 4 counts, whereas C, it is toggling continuously after 1 count. Okay. C is toggling continuously after just 1 count, and A, it is toggling the least. So we will see in terms of frequency also. See, if this is toggling the means if this is toggling the least, so obviously what will happen? Frequency will be maximum where? Frequency will be maximum where? Can you tell me? It's okay. It's okay. At the moment, just understand this. See, if this is the time period T, if each of the clock pulse has time period T, so time period of this will be what? You can see this is getting repeated after 2t. Okay, this is getting repeated after 2t, and this is getting repeated after 4t. So the maximum frequency, if frequency of the clock is f clock, so over here this will be what? F clock by 2, and over here it will be what? F clock by 4. So the frequency of toggling, it is more always in your LSB, and the frequency of toggling in MSB, it is the least. So this might be asked, where is the toggling frequency more or where is the toggling frequency less? So you need to say that your toggling frequency is least at MSB and it is maximum at LSB. So over here, the frequency will be what? It will be f clock by 4, and if you take output means frequency from here, so this will be f clock by 2. So sometimes such kind of circuit are also known as frequency divider circuit. Why? Because you are seeing you can divide the clock frequency in any multiple of 2 frequency. This is 2 to the power 1, 2 to the power 2. So in the next case, we are going to see that we will be dividing it in your 2 to the power 3 also. Okay. So this is what? Still I haven't told you what is the count sequence. So this is your MSB, this is your LSB. So let us very quickly see what is the count sequence over here. So at 0th clock pulse, it is 0, 0. In the first clock pulse, this will be 0 1. You can see 0 1. In the next clock pulse, it will be 1 0. Next clock pulse, it will be 1 1. Then again you can see 0 0. So this is what, this is your mod 4 up counter. Mod 4 what? This is your mod 4 up counter. Now here in this particular case, we have taken output from your non-complemented variables. If we had taken the output from this QA QB, so simply whatever will be your output at this QA Q means QB QA, just the complement we will get over here. So initially we were getting 0 0, so here it will be 1 1. So take complement of the state, so this will be what? 1 0. Complement of the state, so that will be 0 1, and complement of this will be what? This will be 0 0, and this will return back again to 1 1. So this is what mod 4 down counter. So anyone have any doubt? Till now I haven't said the shortcut trick how to identify this. I will tell you how to quickly identify by looking into a counter whether it is up counting or down counting. Okay, tell me if this is clear or not. Up to this point, is it clear? Any doubt? Okay, so here you can see what, that basically if we have one flip flop, let me write it in the next page. If we have one flip flop, so the maximum number of countings that we can do is 2 to the power 1. Okay, so we are able to count exact means unique two states. If we have two flip flop, so the total number of unique states is what? 2 to the power 2. So 4 states. When we have 3 flip flop, so the total number of unique states will be 2 to the power 3. So that will be 8 states. So over here it will be 0 to 1. Over here it will be 0 to 3. Over here it will be 0 to 7. Similarly for n flip flop, basically it will be what? 2 to the power n state. So in total there will be 2 to the power n states from 0 to 2 to the power n minus 1. Okay, 2 to the power n minus 1 states we will be counting. Okay, fine. So now let us take this. Okay, very quickly I want you to first sketch the diagram and then tell me what will be the counting sequence over here. So again you can see we have A flip flop, B flip flop, C flip flop. Okay, so this is QA, this is QB, this is QC. Okay, and external clock is supplied to this one. Okay, external clock is supplied to this one. One more way you can also identify MSB and LSB is that the flip flop where we apply the external clock, that will be your LSB, and the flip flop that is farthest from the external clock, it will be your MSB. Okay, so this is your MSB, this is your LSB. So very quickly copy this down and sketch your output for QA, QB and QC. Quickly do that. So QA is what? It is your negative edge. So if I assume that the initial states are 0 0, so it will keep on toggling like this. Okay, so your next flip flop QB, so this is QA, So QB is what? Basically the clock of QB is your output, normal output of QA. So the negative edge, okay, negative edges. So let us search the negative edge. So these are your negative edges. So QB, it will be something like this. Okay. Next is what? Next is your QC. So the flip means the clock for QC is the negative edges of the normal output of QB. Okay. So normal output. So negative edges means this is your negative edge. This is also your negative edge. So all those places your output will toggle. Okay. So let us write the states first. So this is 0, 0, 0. Okay. These all states we have over here. Now the counting sequence is what I have already told you, that this will be MSB, this will be LSB. If your clock frequency is FCLK, so over here, if this is time period is T, so over here time period will be 2T. Over here it will be 40. Over here it will be 8T. So obviously, if this is F clock, so over here frequency will be F clock by 2. Over here it will be F clock by 4, and over here frequency will be F clock by 8. Okay, fine. And your counting sequence will be what? It will be 0, 0, 0, then 0, 0, 1, then your 0, 1, 0, then 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1, then again back to 0, 0, 0. So this is your mod 8 up counter. Now similarly, if you take output from QC complement, QB complement, QA complement, it will be what? Mod 8 down, mod 8 down counter. Okay, mod 8 down counter. Okay, any doubts in this? Any doubt? Any doubts? Srihari, Mangesh, any doubt in this?
No doubt, sir. All clear.
Okay, fine. So now tell me one thing. Can we have frequency something like this? F clock by 5 or F clock by 6, something like this. Can we have? Means where F clock is what? F clock is the frequency of external clock. Okay, external clock. So can we have frequency like this? Can we have frequency like this? Tell me, can we have frequency like this? Yes, we can have frequency like this also. Suppose, see, when I had written this, this is what? This is your mod 8 up counter. So the frequency of C is what? F clock by 2. Frequency of MSB is what? F clock by 8. Now see very carefully. If I, for creating F clock by 5, if I create a counting sequence, something like this, okay, if I create a counting sequence like this, okay, if I create a counting sequence like this, so this is what you can see. Your LSB is toggling like 0 1 0 1 0 1 0 1 again from here. Okay, so sorry, very sorry. So this will be what? See, where is this repetition happening? So 0 1 0 1 double 0 1. No, this is not the proper way. So then what is the proper way? 0 1 0 1 0 0. No, this is also not proper. So if I take something like this, see, after this time this is getting repeated. So if your clock frequency is FCLK, so for generating this sequence, you can see this is getting, means one of the state is counted at, this is one time period, another time period, another time period, another. So in total 5 time period are taking place. So what, after what frequency is this getting repeated? F clock by 5. Okay, F clock by 5. Over here, see, in this case, when your counting sequence was like this, so each of the bits they were representing different clock frequency, means different division of clock frequency. Like C was F clock by 2, A was F clock by 8, B was F clock by 4. But look, in this counting sequence, each of the bit will be showing F clock by 5 only. This F clock by 5. Over here also repetition, you can see it will take place after 5 states. So here also it will be F clock by 5. Over here also it will be F clock by 5. So each of the bits it is getting, means it has frequency of F clock by 5, and this is what? This is your mod 5 up counter. So tell me, is this concept clear? That you can have such kind of frequencies also, frequency division. Only thing is that you need to make what? You need to make, suppose if you want to have F clock by 5, so you need to create a mod 5 up counter or a mod 5 down counter. If you want F clock by 6, then you need to create what? You need to create either your mod 6 up counter or mod 6 down counter. Did you understand the concept, Mangesh and Srihari? So Mangesh,
Yes, sir. I understood that, but I have one doubt, like where actually we are using this, like
where,
actually we are using this, like is
what you are using? Means I am not getting.
actually, like, sir, where we are using this state, like this.
What state? Means the practical application of this F clock by 5 or
Ah,
F
yes,
clock
yes.
by 6. See, you need, okay, you always don't need frequency that are divided by 2 or power of 2. Okay, suppose you have 32 kilohertz. Now you always don't want this to be 16 kilohertz, 8 kilohertz, 4 kilohertz, 2 kilohertz, or 1 kilohertz. Okay, you won't be getting 1 kilohertz, 2 kilohertz will be the max. You always don't require something like this. Okay, you always don't require something like this. Sometimes you might require even 20 kilohertz. Okay, 20 kilohertz you might require. So at that time you can take help of such counter and you can get a 20 kilohertz frequency also. Is
So
that?
is it, so is this the basis of what the timers in a microcontroller or something work? We can suitably create the delays.
Yes, T on and T off means that retentive on off timer. And what was the other one? There is this. There were two kinds of timer in your PLC and this microprocessor microcontroller. So
Okay, okay.
I am telling for this means even I forgot means PLC. I also haven't studied from like 2 years. So there is this retentive on off timer. Okay. So usually you're counting like your stroboscope. Do you know the principle of stroboscope or any kind of pick off? Pick off, you know this thing.
No, 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 exactly.
Okay, I will tell you what is this. Suppose there is a fluid flowing through this pipe. Okay, and we have a small turbine kind of thing over here. Okay, so basically what happens when this fluid will flow, this will rotate. Okay, faster
Okay.
the fluid flow, faster will be this rotation. Okay, slower the fluid flow, slower will be the rotation. So this we make actually of a ferromagnetic substance, and we have a pick off over here. This is known as pick off. This is basically doing what? This is of a magnetic material. So it will do what? This is ferromagnetic. So this means basically this pick off, it will be able to count how many blades, means sorry, what is the revolution per minute of this turbine. Okay, revolution per minute of this turbine by counting the blades that are passing per minute. Okay, so how is it going to count? Basically it is going to count with the help of this up counter. It is going to count with the help of up counters only. So now if you ask me where is this used, so sometimes what happens means, uh, if you want to say, so I am also not able to means properly tell you, there are questions like means for what mod you will get, means they will give you something like this, 32 kilohertz. Okay, 32 kilohertz they will give you, and they will ask you either what is the number of states, means clock frequency is 1 kilohertz. Okay, 1 kilo means sorry 1 kilohertz, I am telling this is your clock frequency. And if you have like five flip flops, so what will be your frequency of MSB, or what will be the frequency of LSB? Such kind of things they ask. But I have seen one question where they have made a f clock like this. Okay, f clock like this means suppose if it is your 50, okay, 50 kilohertz clock, and it is said like that this is what, this is your mod 16 up counter, mod 16 up counter, and you require what, you require basically 10 kilohertz of frequency. 10 kilohertz means what? If you divide 50 by 5, then you will get this. So they have asked you what modification should we do such that we get 10 kilohertz. So if you make a mod 5 counter using this mod 16 up counter, you will be getting this. Okay, so such kind of question I have seen, but real life application of this, because we usually don't use all this circuit for dividing the clock. We have 555 timers we can do using that, or even we have oscillators we can create, means different clock frequency from there. but using this particular circuit, we usually, means even I am not able to recall where we use this. Okay, are you getting the point?
Clear, clear.
Okay, so this question, once I have seen, a 50 kilohertz has been given, and basically this is the clock frequency for a mod 16 up counter. You need to generate 10 kilohertz. So what modification you need to make? So if you make a mod 5 counter using this mod 16 up counter, you will be getting 10 kilohertz of frequency at each of the bits. Okay, at each of the variables. So now here I have said LSB is toggling the most and MSB is toggling the least. Already I have told you. And this is what, either we will use normal output for all the flip flop as clock, or complemented output as clock for all the flip flop. Now what do we mean by this? Now there might be some doubt that, sir, here we are using this. Now why can't we use this output as the clock for this one? Instead of normal, why don't we use this output, complemented output of the next stage for the clock? No. Usually in asynchronous counter, we don't do that. If you are taking your clock for the one of the stages from your normal output, then in all the subsequent stages, you have to take the clock from your normal output only. You are not going to change the outputs. Okay, so this is very important. Okay, so now the shortcut trick for identifying, how to identify basically that whether we get up counter or down counter. Okay, up counter or down counter. So look very carefully. In the first case, yes, tell me.
I'm sorry to interrupt, but in the last case, last slide actually.
Mhm.
No, the other one. Yes. One second. Before that,
This one,
this one.
yes.
We have talked about this dividing. Like we can generate any frequency you want.
Mm-hmm.
Uh, in that, after 0000 to 100, then we are actually resetting, right, sir? Resetting to 0 again.
Yes,
So in the normal sequence, we need to do something in the circuit to generate the
to
0, right?
generate this zero once again. We will discuss that. We have this.
Okay.
Okay,
So
we will discuss.
only after that we can generate any frequency, right, sir?
Yes. I just
Oh,
told you at the moment that we can either reset it to the state if this is your down counter, and if suppose this is your up counter. If this is your up counter, so normal up counting sequence will be what? This is your normal down counting. Now suppose if I want to create mod 5, so what I will do? Mod 5 down counter. Okay, so this will keep on repeating then.
sir, actually, in this mode 5 means including the starting stage
Mod
is
5 up counter. Listen, mod 5 up. So over here you will have 0 to 4 counting sequence from 000 to 100. Okay, if it is your mod 5 down counter, then what? Then you will have from 7 to 3. Why? Because 7, 6, 5, 4, 3. So unique states are how many? 1, 2, 3, 4, 5. So this is very important. Okay, this is very important, that whenever we say mod 5, at that time you need to remember mod 5 down counter, that you need to have 5 unique states. Okay, so is this
okay.
clear now?
Clear.
Mod 5 या mod n? mod n. That means you have unique n state including 0. 0 is also one unique state in your counting. Okay.
Okay. Okay.
So now let us try to identify by looking into the circuit how to see if it is up counter or down counter. So I will always tell you what this trick is with respect to your non-complemented output. See, like in the previous case, if we knew that if we take output from QC, QB and QA, if this is your up counter, then it is very means by default we can assume that if we take output from QC, QB and QA, it will be down counter, because there will be only two possibilities. If one of the in output we are getting up, obviously the another output it will be producing down. Okay. So in this trick, whatever I say, it is with respect to your non-complemented output. Now see, if we take, if our clock edge is negative, okay, clock edge is negative edge triggered, so we consider it as negative. If it is positive edge triggered, we consider it as positive. First. Second, output. Non-complemented output, we consider it as positive, and complemented output we consider it as negative. So whenever clock edge and output have same sign, then your normal output is what? Same means it will be down counting. Okay, it will be down counting. And whenever clock edge and output have different sign, normal output will give you up counting. So let us go back in our first case over here. Okay, over here. So look over here. We are taking output from normal. So that means normal, I have told you what, plus, and this is what? This is your negative edge triggered. So negative edge triggered means minus. So positive, negative, they are basically of different sign. So that means what? This will be up counting. Up counting where? At your normal output. So if your normal output is doing up counting, your complemented output will give you down counting. Okay. So you can see over here we have up counting. Now come to your second case, third case. So here also you can see we are taking negative clock edge, and output that is supplying your clock, it is from your normal, so that is plus. Again there is a sign difference. So whenever there is sign difference, I told you what, that this will be basically what, this will be your up counting. So if your normal output is up counting, so obviously your complemented will be what, complemented variable will be giving you down counting. So this simple logic helps us actually to determine very quickly whether your circuit is up counting or down counting. Like in this particular case, if I tell you we are taking output from complemented, so you don't need to check for complemented. First you see clock edge is what, in this particular case clock edge is positive clock edge, as there is no bubble over here, and we are taking output from where, we are taking output from normal variable, so that is plus. Whenever same sign, that means your normal output is giving you what, it will give you down counter. But in this particular question, you have been asked from, means what will be your output from your complemented variable. So you will say what, that this will give you up counting. Tell me if this concept is clear or not. So this is one shortcut trick actually to determine how to, means what will be your counting sequence when you are having a counter, whether it will be up counting or down counting, you can know like this. So Mangesh and Srihari, did we get this concept
Clear, sir. Clear.
clear? So note it down very quickly, note this down. Okay, so now I will be discussing what you had asked me. So note this down very quickly. Okay. So you had asked me, sir, that how to basically create such kind of sequence. Means we need to basically clear. Okay, we need to clear the states of flip flop. So we basically have what? We have asynchronous clear and preset input. See, now we are not going in sorry, your synchronous clear and preset inputs, because that is a concept for gate exam. Okay, and for HAL exam it won't be asked that you have a synchronous clear preset, because that is a very conceptual part, and such kind of questions it won't be asked in your HAL. But they are definitely going to ask you asynchronous clear and preset. Now what is this asynchronous clear and preset? So look very carefully. Suppose if I have a mod 8 up counter. Okay, mod 8 up counter. So in mod 8 up counter, if I want to make it, assume mod 6. Mod 6 means what? From 0 to 7. So 0 to 7 means what? That this will be your counting sequence. Okay, sorry, this is 0 to, it's mod 6 I told na, so 0 to 5. Okay, 0 to 5. 0 to 5, that means what? From here to here, this should be my counting sequence. Now you can see basically that after this state, immediately your count sequence should again return to 0 0 0. So you can see this is already 0, but this two flip output of this two flip flop, which two flip flop? This two flip flop needs to be cleared. Okay, this two flip flop needs to be cleared. Why? Because this is one, this is one. After this you can see this is still one, but this will go to 0 and this will go to 1. But after this state my count sequence should go to 0 0 0. For that to happen, after this count, immediately the output of this flip flop, means if this is QC, QB and QA, QC should immediately go to 0 and your QA should immediately go to 0. So this is done by what? This is done by your clear input. And assume over here, if we have a mod 3 down counter. Mod 3 means what? From 7, 5, 6, again we need to go to 7. So basically this 3 should be your counting state, and immediately after the state you need to come back to this state. So you can see what over here, that if you want to come again back to this state, this 0 should be converted to 1. So basically 0 changing to 1 means what? You are presetting the input, which, sorry, presetting the output. Which output? If this is QC, QB, QA, you are presetting your QB from 0 to 1. So this is basically the work of clear and preset. Whenever you give clear input, it will basically clear all the output of flip flop. Okay, and whenever you activate the preset input, all the output of flip flop, it will go into your set state. Set state means what? It will go to 1. Okay, so Srihari, did you understand this?
Yes, sir, clearly.
Okay, so now let us see what is this clear and preset input. Okay, clear and preset input. So you can see over here that I have one NOR gate. Okay, NOR gate. So this will be what? A plus B whole complement. Now assume if I have A, B over here, and if I give 0 over here. So what it will be? It will be A plus B plus 0 whole complement. So this is actually equal to what? A plus B plus complement. But if I give over here 1, if I give over 1 over here, so what will happen if I give 1 over here? Immediately I have told you, if output of your NOR gate is 1, sorry, if your output, I am telling, if input, any one of the input of NOR gate is 1, immediately you can say that your output is going to be 0. Okay, your output is going to be 0. So now what you have, see, this was initially when we had studied, we had started this chapter from such kind of latch. Then from latch we went to flip flop. We have studied flip flop, but all those things were incomplete. Basically all the flip flop had two more input. One of the input is clear, another input is preset. Okay, another input is preset. Now remember, this clear is connected with your non complemented, and preset is always connected with your complemented. Okay, so here basically we have two inputs A, B. At the moment, this A, B I am not discussing about. Okay, so you can even write this as, I have already told you, as this is your SR latch, so opposite to complement you have set, so obviously this is going to be reset. So at the moment I am not talking about S and R, I am just talking about these two inputs. So the combination can be 0 0, 0 1, 1 0 and 1 1. Look over here, if clear and preset both are 0 0, okay, both are 0 0, then what will happen? If this is also 0, this is also 0, so your latch, it will work normally, normal. Okay, because if any one of the input of NOR gate is 0, it basically depends on your other input for your output. Now look, if clear is 0, preset is 1. So what will happen? If clear is 0, immediately this will go to 0 and this will go to 1. So what is happening? Your normal output is clearing. So this means what? The moment clear input is given high, your clear input is given, sorry, over here I have given preset high, I'm very sorry. So clear 0 and preset high. So when this happens, if preset is high, so immediately if this input of this NOR gate is 1, so output will be 1. If this is 1, so this will be 0. Okay, so this will be 0. So you can see what, basically we are doing what, we are giving preset as 1. So if preset is 1, so you can see what is happening over here. Means I have done some mistake over here or what? Just wait a minute. Preset, whenever it is high, normal should go to 1. So if clear input goes to 1, just give me a minute. I have done something wrong over here. So clear 0, preset 1. It's what I am doing. If this is 1, obviously, so look over here. It's what I am confusing you guys. So if preset is 1, so I told you what preset, what it does, if you apply preset input, It basically what it does, it sets your flip flop to 1 preset. If you apply high, if you apply high input to preset, basically your flip flop or latch, it will go into set state. It will go into set state. Why? In set state, qn plus 1 is 1 and qn plus 1 complement is equal to 0. So whenever you apply preset 1, flip flop will be set. Set state means what? Normal output is 1, complemented is 0. So look, preset 1. So what will happen if you apply 1 over here? If any one of the input is 1, output of NOR gate will be 0. So this is 0. If this is 0, this will be 1. So qn plus 1 is 1. So your flip flop is in set state. Now look over here. If clear input is high and preset input is 0. So if clear is high, this will go to 0. This will go to 1. Okay, if this is 0, obviously this is going to be 1. So over here you can see qn plus 1 is 0. So that means what? Your flip flop is directly in your reset state with the help of this clear. It doesn't matter what is R, what is S, it doesn't matter. The only fact is that if your clear input is high, your flip flop will go to reset state immediately. Now if both the inputs are high, so this is invalid state. Usually we avoid this, we never apply this. Okay, this is your invalid state, we never apply this thing. Okay, is this clear? Tell me if this is clear or not. Is this clear, Shriyari?
Yes, sir. Yes, sir.
Okay, so now with the help of this clear and preset, we are going to see how to basically construct mod 5, mod 6 up down counter. Okay, but before that, see here we have discussed what? Here we have discussed NOR latch. So clear, remember this, if they have said you we have clear input, pre-input, okay, normal. So this implies that this is for your NOR latch, that your internal circuit is based on your NOR latch. Now what will happen if we have NAND latch? So I have already told you, in NAND latch, if we have a NAND gate AB, so output will be what? A dot B whole complement. Okay. Suppose if we have AB over here and one of this input is 0. So it doesn't matter whatever is your output, okay, whatever is your input, your output is always going to be 1. Okay. So in NAND, basically 0 has more priority. Okay. 0 has more priority in what? In your NAND gate. Okay. Just give me a minute. I am getting one call. Okay, so here I told you what? 0 has high priority compared to your 1. So when do we use clear bar and pre bar? Whenever we have your NAND latch. Combination can be 0 0, 0 1, 1 0 and 1 1. Okay, 0 0, 0 1, 1 0, 1 1. Okay, fine. So now look over here. If both the inputs are 0, clear bar and pre bar, basically this is what? This is active low input. Okay, active low input. So whenever both the pre and clear are applied simultaneously, so this is invalid. We usually avoid this. Now look, if clear bar is 0 and pre bar is 1, so if this is 0, immediately this will go to 1, and if this is 1, this will be 0. Okay, if this is 1, this will be 0. So this is what? Qn plus 1 is equal to 0. Okay, so that means this is in your reset state, and you can see from here that as this is active low, you are applying input to clear bar, So obviously it will clear your flip flop. So clear means what? It will be in reset state. Now the second case is what? That when you apply preset as 0 and clear as 1. So when you do that, this will go to 1, this will go to 0. So this is what? Qn plus 1 is equal to 1. This is your set state. Okay, set state. So you can see over here that preset, active low preset has been supplied with your input, because 0 is input for active low. So that is why this is setting your flip flop. So you can see over here. And if you apply 1 1, this will be simple. It will continue, no change, or it will be simple in your hold state only. It is not good actually to write hold. It will be normal operation. Okay, normal operation of flip flop. This will go on. So tell me, did you understand this clear bar, pre bar, and clear and pre? So clear and pre, it is going to be used when we have your internal circuitry as NOR, and this clear bar and pre bar, active low clear and active low pre, it will be used when your internal circuits are your NAND gate. Tell me if this is clear or not. Is this clear?
Clear, sir.
Okay. So now we have one of the counter, something like this. Now basically we need to find out what is the mod of this counter. So first we have to identify that whether this is your up counter or down counter. So for doing that, you can see that this is negative edge clock. So negative edge, so this implies what? Negative. And clock is being supplied from normal output. So that means what? Normal output means plus. So this is different in sign. That means this is up counter. Up counter. This is your what? This is your up counter. But here you can see we have some clear inputs also. We have clear input. Now when is this clear input going to be activated? As this is active low, so whenever input of this, any one of the input of this means, sorry, when both the inputs are 1 1, at that time what will happen? We will get 0. Okay, whenever both the inputs are 1, then only we will get 0. If any one of the input is 1, another is 0, we will always get 1. So 1, this is active low clear. Active low clear will be activated when it gets 0 as its input. So we can also make a conclusion over here that all this JA, JB, JC, they are constructed using your NAND latch. Okay, so let us then write the counting sequence, normal counting sequence. So QC will be MSB, QA will be LSB, and let me assume output of this gate is X. Okay, output of this gate is X, and X is equal to what? X is equal to QC and QB whole complement. So normal counting sequence will be 0 0 0 0 0 1 0 1 0. Okay, so let us simultaneously do this also. So when we have this, so this will be 1, over here 1, this will be also 1, because we need to do NAND operation of QC and QB. This will be 0 1 0, so this is also 1. Next will be 1 0 0, this is also 1. Next will be 1 0 1, this will be also 1. Next counting state will be what? It will be 1 1 0. See, immediately you have 1 1 0. What will happen? This will go to 0. Now the moment this is 0, all the flip flop will go into clear state. So now there is one confusion among students, that whether this will be a valid counting state or not. Tell me. Shriyari, you want to say that whether this will be a valid counting sequence or not? Hello.
Just looking, sir.
See, did you understand up to this point?
Sure, sure, sure.
Okay. So I am telling that immediately after you encounter the state, what will happen? Your clear input will be 0, 0, 0, and immediately QA, QB, QC, it will go back to 0, 0, 0. All the states will be clear. Okay, all the states will be clear.
So,
So that is what I am.
it's actually, yes, it should be a valid state because before that, I mean, the- all the state takes a particular time to happen, and but only after this 110, it's going to 000. It that should not be on that.
See, I haven't told you that whether this is your practical cases or not. See, in HAL exam, they are not even going to ask that much that if this is practical or not. See, I will tell you.
Okay,
If this is asynchronous clear pre or asynchronous clear bar or pre bar, this state will not be counted in your sequence. The moment you get this, so this is your total mod. So this is what 1, 2, 3, 4, 5, 6. So this is a mod 6 up counter. Okay, mod 6 up counter. Now we are not going in that much depth. If it is said that this is your, if it is said that this is your synchronous clear pre clear bar pre bar, okay, if it is said synchronous, then what you are going to do, you are going to calculate like this only, but then the state at which this transition is taking place, this will be also valid state. I am not going into depth, I am just telling that at that time, if you have synchronous clear in the same question, if I had told you that if this clear was synchronous, then your answer would have been what? It would have been mod 7. So in synchronous counter, your count is always one greater than your asynchronous counter. Just remember this. Okay. Is this clear? Clear, Shriyari?
clear, clear.
So remember, in asynchronous, the state at which you are getting your clear clear bar, pre bar activated for the first time, that state will not be counted. But if it is your synchronous counter, means synchronous clear clear bar pre bar, at that time the state at which transition is happening for the first time, that state is going to be a valid count state and you are going to take it. So make a note point of this. This is very important. Okay, so this is one more question. One more question. Tell me what will be your answer now. This you are going to solve. So such kind of question will be asked because this will take very less time to solve. Very quickly solve, Shriyari. See, first you need to identify that whether this is up counter or down counter. But there is one more very simple trick. Here it is given that it is pre. So always remember that clear is used with up counter and pre is used with down counter. Why? Because if you want to clear something, what will you clear? Here these are binary state, so only thing you need to clear is 1 to 0. So you are clearing 1 to 0. So if you are returning again to 0 0 0, that means this is what you will be counting upwards. And if you are presetting, so that means what you will be presetting? So basically you will be presetting 0 to 1 only. So if you go to 1 1 1, that means you will be counting downwards. Okay, you will be counting downwards. So here let me write this as QA, QB, and QC. So write the count sequence QB, QC. Again, let me take this as X.
The count sequence should be QC, QB, QA.
Yes, sorry. QC, QB, QA. So normal count sequence, what is X? X is QC plus QB. Okay, and this is what? This is pre-bar. So pre-bar means what? Active low preset. So over here it will be what? This will be 1, this will be 1. Next count sequence will be what? It will be 1 0 1. So again over here this will be 1. Next count sequence will be 1 0 0. Again this will be 1. Next count sequence will be 0 1 1. Again this will be 1. Next count sequence will be 0 1 0. So again this will be 1. Next count sequence over here will be 0 0 1. So over here you will be getting 0 for the first time. So this will not be valid state. Immediately your flip-flop will be presetting. So what is the mod? 1 2 3 4 5 6. So again this is mod 6 down counter. Okay, so this is your mod 6 down counter. I have designed using pre-bar input. Okay, tell me if this is clear or not. Is this clear?
Sir, one
Yes.
doubt, sir.
Yeah.
Um,
Hello,
actually,
I can't hear you. I can't hear
actually,
you.
when will this get reset, sir?
When will what get reset?
I mean, the X, this QB plus QC. I mean, QB XOR QC. So
So
both
this is NOR. Sorry, I'm telling NOR. This is simple OR.
okay.
OR.
So both should get 0 to get a.
Yes. When both QC and QB is 0 for the first time in your normal counting sequence, at that time it will get reset.
So that means in the fourth itself, it should get reset, right, sir? Like
Where? Over here.
fourth one. Yes.
Over here. So if you add QC plus QB, this will be 1.
Oh, QC and Q. Okay, okay. I took
QC.
QB and QA. Okay, okay.
No,
Sorry.
no, don't take QV, QA, okay? So here I have explicitly drawn it using another color, okay? You can see green color this is, and this is another color, okay? So don't get confused, okay? So such
Sorry.
kind of question, it's okay. So such questions will be asked in your HL exam, and you will be able to solve also. It is very, very simple. So is this clear? Is this clear?
Okay, please.
Okay. So today you do what? You go and solve all the questions like this. Okay, you solve such kind of question, and even if you don't solve question, if you have understood this concept, just make proper notes of this, you will be able to solve each and every question of HAL. Okay, so next is what? Register. So register is what? It is used to store multiple bits. Okay, registers are used to store multiple bits. So in register, what basically happens that your bit shifts one flip flop to another in a particular direction. Okay, so it flows from one direction to another direction, and in a particular direction our data flows. Okay, so one means such kind of registers are known as shift register, where your data basically it is shifting from one flip flop to another flip flop. Okay, so that is what shift register. Now we have basically four kind of shift register. One of them is CISO, serial input serial output. What do we mean by serial input serial output? That serially one by one of the input is entering and one of the output is exiting through one of the flip flop. So such kind of shift means register is known as what? CISO shift register, that serial in serial out. Next is what? We have serial in parallel out. So serial in parallel out means what? That serially one by one your input is entering the register, and parallel out means what? That all at a single time is basically what? It is going out of your flip flop. Okay, one means at all means wait, I will just explain you this with one example. So then it will be better, means easier for you to understand. So look over here. So all the flip flop are initially 0 0 0. Now suppose if I want to enter this data 1 0 1 in this flip flop. So this is what? This is your clock, and this data needs to enter over here and it needs to exit from here. So at your first clock pulse, what will happen? This one will enter in this flip flop. This is 0. This is 0. So I will be drawing it over here. So clock pulse over here I am writing. This is QA, sorry, QA, QB, and QC. Okay, QC. So look over here, output is being taken from QC. So at clock pulse 0, QA, QB, QC are all 0 0 0. At clock pulse 1, what will happen? This first data, it is going to enter in DA. So that will be 1, this will be 0, this will be still 0. In the second clock pulse, this one will go to QB, and this next data bit will enter QA. So this will be 1, this one jumped over here. Okay, this is still 0 because this 0 is entered over here, and the next data bit is 0, so this will enter. In the third clock pulse, what will happen? This one will come over here, so this will be 1. This 0 will come over here, so this will be 0, and this last data bit it will enter, so this is 1. So you can see all the data have been entered in your flip flop. Now at fourth clock pulse, what will happen? This one will basically exit from QC. Okay, and over here these are all now 0 0 0 0. No more data bit are present. So what will happen? This will be 0, this one will shift over here, this 0 will come over here, and this one is out of the register. In the fifth clock pulse, what will happen? Basically this 0 will come over here, this one over here, and this 0 will go out. So this 0 over here, this one will come over here, this 0 and this 0, and in your sixth clock pulse even this one will go out, and again all the bits it is going to be 0. So this is what? This is basically serial in parallel out. Okay, serial in, parallel out. Sorry, serial in, serial out. So one by one your data was entering, and one by one your data came out of your flip flop. Now next is what? Serial in, parallel out. Okay, serial in, parallel out. Now what do we mean by this? So serially we are entering the data, and parallelly means what? At just one clock pulse our data is exiting the all the registers. So you can see, look at this clock pulse 3. Okay, look at this clock pulse 3. So at clock pulse 3, what is happening? That if you take output from all this flip flop, so over here this is 1, this is 0, this is 1. So you can see you are getting the data simultaneously at your third clock pulse. So this is what? This is your serial in, parallel out kind of your shift register. Okay, serial in, parallel out kind of shift register. Now next is what? Parallel in, serial out, parallel in, parallel out. So this two we don't have in our syllabus. So we are not going to discuss this. Okay, serial in, parallel out. We are not going to discuss this because it is.
Sir, I can't hear your voice. Hello.